So A is the crack length, and if that is B is thickness, the product of B thickness into the crack length will be area. That is the area of the crack length. So that is called energy. How much work per unit area I am giving, and that is used for storing elastic energy, plastic energy distribution. For brittle materials, this part will be zero. Okay, zero. And then this is nothing but surface energy. And for slow process, as I told, kinetic energy is zero. So these are the three heat storing part. And this is how the work is going. So always there is a balance between external work and the internal storage. And you know that the brittle material, this is zero. So we have only elastic strain energy and the surface energy. Okay. So what work you are giving, so basically it is being stored, and if it is exceeding the surface energy, the crack will propagate. So to make it the further clear. So you know Griffith used the concept of potential energy. So a potential energy nothing but the difference of the strain energy, elastic strain energy, okay, minus work done by the external forces, okay. So geometry. So I take the infinite body with a central crack of length 2a. So this is sharp crack, and thickness is d, okay. And you can say you are applying remote stresses sigma, okay. So I want to know at what value of remote stress, that is called nominal stress or remote stress sigma, the crack will propagate. Okay. So as I told, when I am applying remote stress sigma, I am giving the energy into the system. Okay. Now this energy basically the strain energy minus work done by external forces, that is potential energy. That rate of potential energy, rate means with respect to area, that is the area crack propagation. If that exceeds the surface energy, that is rate, okay, then that is my criteria for the crack initiation in brittle material. So for brittle materials, I told that there is no plastic deformation. So I can write del phi by del A, this equal to d u gamma. Basically, this is surface energy. Gamma stands for surface. U is the energy. Del by del A. Okay. And B in the denominator, B is actually it is for unit area. D capital A. Which is, I can write D capital A is nothing but D, thickness capital V into delta A. Okay. So my criteria that energy required to form new surface means basically for brittle material, formation new surface nothing but crack propagation. Okay. So minus criteria is minus del pi del A equal to 2 gamma S, because U gamma is nothing but 2 gamma S into area. Okay. And where the 2 come because two surfaces will form. One is upper and one is lower. And gamma is the surface energy, which is nothing but energy required to break the bond. Okay, in brittle material, the crack propagation by breaking the bond. So and English on scientist, he calculated that potential energy for in a body for a crack length A minus potential without crack. The difference is nothing but minus pi sigma square A square capital V by E, where E is Young's modulus of material, sigma is the applied nominal stress, A is the crack length, B is thickness. So if you substitute this potential energy and difference with A is the area, which is nothing but product of thickness B into crack length. Okay. So if you differentiate, we get pi sigma square A by E. Okay, this is the energy release rate, potential energy release rate. Okay, which is proportional to sigma square. Okay, and so this for crack initiation should be equal to 2 gamma S. This is for now it is for unit area. So total energy for crack propagation 2 gamma S into area. So when you differentiate it, the area goes away. Gamma S is a constant. So the criteria for crack initiation or propagation in brittle materials by Griffith. So this is called Griffith theory. So pi sigma square by equal to constant. So that's why in the beginning I was telling, Griffith found that the product of suppose I make square root of it, then pi e are all constant. So stress into root over A, this becomes constant. So everything I take in right hand side and make square root. So the sigma into root A, this becomes constant, which only depend on material property. Okay. So this is the stress that factor. This is also factor stress sigma F, which is nothing but it. Again, I am telling you this is not the crack tip stress. Near the crack tip, the stress will be very high. It is in fact theoretically it is zero. It is infinite. But this what I am interested is the stresses, how much I have to apply remotely, that nominal stress away from the crack, which will make my crack to propagate. So in fact, Griffith demonstrated it through experiment, So he took several glass pieces, glass rods for different crack lengths. Okay, and he put different amount of load, and he found it out that the product of remote stress into root over A is constant, which is a material property. And then that root sigma into root over A, he called it as into some geometry factor, because for a infinite body with a central crack, the geometry factor is 1. Okay, but if it is the crack is on one side or is some bending, etc., there will be some other factors will be there, which is more, different from 1. So he universalized it. Okay, he generalized it. So he told that any remote stress sigma into root over of pi a. Okay, that is pi into crack length. This is for crack to initiate, this has to reach a critical value, and he called it a critical stress intensity factor of K1C. Okay, that is how the concept of K1C came, and by through experiment you can also evaluate the K1C value. So when you do, if a material is brittle or you are using concept of LEFM, linear elastic fracture mechanics, so that material parameter, critical stress intensity factor K1C, one start from mode 1, that you can determine from experiment, and as you know it is just a material property, it doesn't depend upon the geometry, then you can use it also for your own component. Okay, that is how the fracture mechanics concept is applied for knowing whether crack is stable or whether you can apply allow it or not. For example, in case of nuclear vessels, for boiling out of type of reactor, we have a nuclear vessel where over the period of time the crack can form. Okay, due to several regions, and because of neutron irradiation, the material becomes brittle. Okay, so we can safely use the concept of linear elastic fracture mechanics. So what do we do? You see, the vessel, suppose you cannot do a test to know whether crack is going or not. Okay, nobody will allow to do that. So how to know that whether the vessel is safe or not for operation? So the same material, okay, you do the test. Of course, it has to be irradiated material. You do the test and you calculate the critical stress intensity factor K1C. So that becomes your material property. And then in your actual your vessel, you model how much stresses comes because of the loading condition, like internal pressure or some axial load or thermal stresses, and then you know the crack length. Then you multiply that remote stress in crack length, and you also multiply by geometry factor, so which is other than 1. Okay, quite different from 1, and that is called K1. That is applied stress intensity factor. That is our loading parameter. If that factor is less than the material value that we have determined in the lab from a small specimen, then the crack is safe, you can allow it to operate. If it is not, okay, then you can tell that the crack can grow. If it is not, it is unsafe. Okay, so this is the concept of linear elastic fracture mechanics, which is now widely used. Now, there are some limitations. Okay, so why we are now studying the plastic zone, effect of plasticity and elastic plastic fracture mechanics is there. In actual reality, material, for example, in case of pressure vessel steel, okay, or stainless steel, so the materials are not very brittle unless it is a lot of see, for example, the pressure vessel steel, which is a low alloy steel, so they are initially moderately ductile. They are not brittle. They fall into class of ductile materials. But over the period of time, that is when neutron irradiation takes place, they become brittle. Brittle means they lose their ductility. It is not brittle. They become less ductile. So for those materials, you can apply the concept of linear elastic fracture mechanics. But still, when the ductility loss is not large, okay, then the material reform also plastically. For example, near the crack tip, the stresses will be high. So when the stresses will be high, your equivalent stress, which is required for plastic yielding, they will be exceeding yield stress. So near the crack tip, there will be some plastic deformation. Whatever you do in case of ductile material. Now, one plastic deformation occurs, so that is then you know that you cannot apply the concept of LEFM, but that is a catch here. In the sense, if the size of the plastic deformation zone near the crack tip is very, very small, okay, it is approximately around 2% of the other dimension, let us say 2% of the thickness, okay, or 2% of the crack size, approximately this is the number I am telling, 1/50 or 2%. Then, if you apply the concept of LEFM, that is the stress intensity factor K1, then it will not be very far off. Okay, it will still be close to the exact solution or good, close to the actual situation. So, LEFM try to take advantage of the situation where plasticity is very small. Okay, that is a limited plastic deformation in the material. So, we will be talking those cases. Means material is not fully brittle, means it is not totally elastic, that some plasticity is there. So, no matter what you do, you cannot avoid it because material is ductile. However, we will try extend the concept of linear structure mechanics to this class of material where plastic deformity is unavoidable, means it will be there, but it will be very small. So, if it is very small, then how to take care of that? Okay, how to take care of the plastic deformation in the calculation of the stress intensity factor. This is where the Irwin's correction, so I was talking Irwin's correction came. So, what Irwin did is that he estimated the plastic zone size. Plastic zone size means it is the region in which plastic deformation occurs. Okay, so radius is plastic zone, and he assumed that because when that is plasticity is occurring, so material will deform. For example, material is elastic perforated to plastic. Plastic means there is no hardening. Then that portion will just try to open as if it doesn't have any resistance because it is a it is no hardening is there. So that extra zone, that is plastic zone RP, he added to the crack size. So it is as if we have a more crack which is extended or which is increased because of the plastic zone. So that you must have already studied in the previous lecturer, Suranjit, he must have told you that instead of crack length A, I will use a effective crack length which is A plus RP. Okay, RP stands for radius to plastic zone. So we will see then how to estimate. We have to calculate now stress intensity factor K1, which is nothing but sigma root over of pi, and instead of A, I will use A effective. Okay, that is my the effective stress intensity factor, taking into account the correction of the plastic zone. So how to then calculate A effective, which is A plus RP. So you must estimate the plastic zone size RP. Okay, so there are different concepts for estimation of plastic zone size. One of the concepts is Irwin's concept, which is one-dimensional solution. So I will talk about some more one-dimensional, also two-dimensional solutions, and some more elegant solutions for the plastic zone, which will help in estimating the effective stress intensity factor. But later you will see if the this is for limited plastic. As I told, the radius of plastic zone could be around 2% of the crack length. If it is or thickness or remaining ligament, whichever is smaller. If it exceeds that, then the concept of linear elastic fracture mechanics you cannot no longer you cannot use. You have to go for further other elegant parameters like J integral. Okay, so we will be talking about that concept later, which is falls in the category of that elastic plastic fracture mechanics. So now we are talking about the extension of the linear elastic fracture mechanics criteria for small cell yielding, where the radius of plastic zone is very small. Okay, very small. When I tell very small, it is around 2% of the dimension, whichever is smaller. Dimension is either crack length or thickness or remaining ligament, whatever it is. Okay. So to summarize, for plane stress condition, so you are aware of plane stress and plane strain? Yes. Ready?
Yes, sir. Yes, sir.
Yes, sir. Okay. What is? Can you tell me what is plane stress and plane strain condition?
Plane condition is stress in the z direction is 0 where the material is very thin. In strain condition, there is no elongation in the z direction because the material is very long compared to the other dimension.
Excellent. Okay. How does it affect the fracture mechanics?
Sir, for plane strain condition, the crack propagation is more compared to the plane stress condition, or something that was discussed in class.
Yes. So when there is a plane stress condition, it is basically thin, but sheet is thin. So if the material is ductile, okay, so that will be plastic deformation. So plastic deformation process will try to make the toughness more. Okay, but when there is a plane strain, that is thickness is larger, then plastic deformation will be small. Okay, because of the third dimensional stress, it will try to restrict the plastic deformation. So in that case, the fracture